Noche cósmica.
Imagine a place so far from any star that the light taking the longest journey to reach you departed before your species learned to write. Imagine standing on solid ground, your feet pressed against stone and ice, and looking up to see not the warm, familiar disk of a sun, but only the thin, distant prick of starlight scattered across an endless dark. This is the home of rogue planets. These are worlds that drift through the vast nothing between the stars, untethered and alone, moving through a silence so complete that it seems to swallow sound itself before it can even be born. For most of human history, we assumed every planet was bound to a star. We saw ourselves circling the sun, watched the night sky resolve into recognizable constellations, and thought the universe arranged itself around these bright anchors of light and warmth. But what if there were worlds that never knew a star's embrace at all? What if, right now, in the darkness between the galaxy's arms, countless planets are drifting through the cold, their existence so invisible to us that they might as well be ghosts moving through an abandoned house? This is the question that leads us into a journey through rogue planets and the profound quiet they inhabit. If you find yourself drawn to the gentler side of cosmic mysteries, to the strange comfort of thinking about worlds that move unseen and untouched by the usual rules of solar systems, if you want to explore more of these slow, meditative facts about the universe's hidden wanderers, consider subscribing for more journeys through the galaxy's quietest, loneliest places. But let us begin where these worlds truly live. Let us drift outward, away from any sun, into the black. The darkness of interstellar space is unlike any darkness you have ever imagined on Earth. In the deepest cave, in the cloudiest night, there is always some faint glow, starlight from above, or the dim luminescence of city lights at the horizon, or the distant haze of a galaxy too faint to see directly, but present nonetheless. But between the stars, in the vast spaces where no gravitational anchor holds sway, the darkness becomes almost physical. It presses in from all directions. It is not the absence of light so much as the presence of emptiness. A rogue planet drifts through this darkness at a steady pace, moving sometimes at 30 or 40 kilometers per second through the galactic void. Though this speed is so incomprehensible over the scales we normally think in that it registers almost as stillness. A rogue planet might take 10 million years to travel a distance that light covers in a single week. Imagine something so patient, so unhurried, that time itself seems to lose meaning around it. The cold is equally absolute. Without a nearby star radiating heat, without any source of external warmth, the surface of a rogue planet reaches temperatures that most of us have never truly felt, not even in the harshest Antarctic winter or on the highest mountain peak. These worlds know a cold that numbs the mind to consider. If you were to stand on such a world, if such a thing were remotely possible for a human, the cold would penetrate not just your body, but your sense of what temperature even means. It would redefine cold itself as something far more final and complete than you had ever conceived. Yet this cold is not uniform. The farther you travel from the galactic center, the colder it becomes still, because the faint ambient warmth of the galaxy's starlight, so distant, so scattered that it barely registers as energy at all, decreases with distance. Some rogue planets drift in regions so remote that the starlight reaching their surfaces has diminished to almost nothing. These worlds know an isolation that becomes almost incomprehensible. And yet there are no storms in this darkness. There is no wind, because wind requires an atmosphere being pushed by heat and pressure differentials. There is no sound at all. There is only the profound silence of a world moving through a void where nothing touches it, nothing reaches it, nothing speaks to it, except the slow pulse of its own internal gravity, holding it together in an embrace that is eternal and utterly solitary. This is the space that rogue planets call home. This is the medium through which they travel. And perhaps most remarkably, these journeys have been happening for billions of years. For as long as planets have existed in this galaxy, some of them have been cast loose from their original orbits, ejected from the solar systems where they were born, and sent drifting into this endless night. They have been moving alone and unseen for longer than human civilization has existed, longer than the entire history of Earth, even longer than the age of the dinosaurs. Some of them were already ancient when our sun first ignited. Think of it this way. For every star you see in the night sky, for every point of light that anchors a solar system, there are believed to be between 1 and 10 rogue planets drifting in the darkness nearby. The universe is populated far more densely with these lonely wanderers than with the bright, warm stars they once orbited. The cosmos is far lonelier than the constellations suggest. The universe is far quieter than we have typically imagined. As you consider this, as you sit with the knowledge that there are more worlds drifting through the dark than there are stars shining in the sky, notice how your breath settles. Notice how the image of something so ancient, so patient, so utterly alone and undisturbed for billions of years can become somehow soothing rather than frightening. There is a strange peace in the thought of a world so removed from chaos, from collision, from the turbulence of orbits and the demands of a nearby star. There is something profoundly still about imagining rogue planets moving through their darkness, untouched, eternal, serene. The silence between the stars is profound, and rogue planets move through it like ships on a windless sea, their journeys marked only by the slow turning of ages. And so we drift deeper still, leaving behind even that faintest ember of distant starlight, into a silence that most worlds never know. What we are approaching now, what we are about to understand, is something that challenges the most fundamental assumption we might make about planetary existence. For nearly all of human history, planets were simply the attendants of stars. They orbited, they danced. They belonged to something larger that gave them purpose, warmth, definition. But what if we removed that assumption entirely? What if we imagined a world cut loose from any star whatsoever, cast out into the absolute darkness between suns, orbiting nothing at all? This is the rogue planet, and it exists, not as speculation or mathematical ghost, but as a genuine category of world that our universe has created, and in remarkable abundance. A rogue planet is, quite simply, a planetary mass object that does not orbit a star. It travels instead through the interstellar void, bound to no sun, receiving no steady warmth from any distant fusion engine. It is a world in permanent night, not the temporary darkness of a planet's evening side, not the seasonal dimness of a world far from its primary, but true and endless night. The kind of darkness that has no cycle, no promise of dawn, no schedule of return. It simply is, cold and isolated, moving through the galaxy according to the slow, patient mathematics of gravity and momentum, following a path that no one ordained and no celestial mechanics dictate except the inertia of its own existence. When astronomers first began to seriously entertain this idea, and we will come to how they did so, there was something almost melancholy about it. A planet, after all, seemed defined by its relationship to something larger. A planet orbited. That was part of what made it a planet. And yet, as we have learned more about how solar systems form, how they evolve, how they sometimes shatter under the weight of their own gravitational interactions, we have come to understand that rogue planets are not aberrations or impossible things. They are common. They are ordinary in the grand scheme of cosmic processes. They may, in fact, outnumber the stars themselves. Consider for a moment what this means. Imagine all the stars you can see on a clear night. Imagine all the stars in our galaxy, hundreds of billions of them. Now imagine that for every star, there may be several planetary wanderers drifting through the darkness with no sun to call home. The sheer scale of it, the profound loneliness of it, and yet also the strange ordinariness of it. This is what awaits us as we turn our understanding toward the rogue planets. These worlds are not heated by stellar radiation. They do not warm themselves at a sun's fusion furnace. And yet they are not entirely cold in the way we might imagine. A rogue planet, particularly a young one, glows faintly from within, the residual heat of its own formation, still radiating out into the void, a slow ember that has been cooling for billions of years and will continue to cool for billions more. This internal heat, this ghost of its birth, gives it a faint infrared signature, a whisper of warmth that sensitive instruments might detect across the immense distances between worlds. The definition itself carries weight, a planetary mass object that orbits no star, not a star that has been dimmed or hidden, not a planet temporarily separated from its system, a world that never had a stellar companion, or that was ejected so violently from the system of its birth that it will never return. A world whose gravity has no master, whose motion follows no predictable orbit, whose sky holds no primary source of light. This is the essential, beautiful simplicity of what makes a rogue planet a rogue planet. And what becomes clear as we contemplate this definition is that these worlds represent a kind of freedom that most planets never experience. They are not locked into the rhythms of a star. They do not experience seasonal variations of stellar heating. They are not gradually drawn into the eventual fate of their sun, whether that is a peaceful dimming or a catastrophic expansion. They are, in a profound sense, independent. They drift through the galaxy on their own terms, tethered to nothing, bound by nothing except their own inertia and the subtle gravitational pull of the galaxy itself, that vast and invisible architecture that holds everything together without demanding allegiance to any single center. If you find yourself drawn to these quiet wanderers, to the idea of worlds moving unseen through the cosmic night, to the slow unfolding of how we detect and understand such solitary travelers, there is more to discover. If you would like to journey further with us through these slowest and most mysterious corners of space, through the detection methods and formation stories, through the strange possibility that some of these rogue worlds might harbor hidden oceans, through the sheer staggering scale of how many such planets might exist around us, then consider subscribing to follow our deeper explorations into the quietest mysteries that orbit no star and acknowledge no sun. We have only just begun to understand the rogue planets. There is so much darkness yet to illuminate, so many solitary travelers still waiting to be mapped and known. And each discovery, each new detection, each refined estimate of their numbers and nature reveals something profound about the universe we inhabit, not as a place of rigid, orderly celestial mechanics, but as something far more wild, more complex, more beautifully strange than we ever imagined. The idea came quietly, almost as an afterthought, in the minds of astronomers who were beginning to understand the true nature of gravity itself. Long before anyone could actually see a rogue planet, long before telescopes grew sophisticated enough to detect such invisible wanderers, mathematicians and theoretical physicists were already penciling out equations that suggested something profound and, in a way, rather lonely. What if a world could be torn from its orbit by the gravitational pull of a passing star, or flung outward during the chaotic youth of a young solar system when planets were still settling into their final arrangements? What if the mathematics of gravity, which governs everything from the smallest falling apple to the dance of galaxies, could permit such orphaned worlds to exist? The 20th century was a time when astronomy was beginning to shed its purely observational skin and become theoretical. Physicists were learning to trust the mathematics, to believe what the equations told them even when their eyes could not yet confirm it. And the equations, as it turned out, were remarkably clear. Gravity did not require a sun merely shaped the stage. A planet could be ejected from its birth system through a gravitational encounter, a near miss with a sibling world perhaps, or a close brush with a passing star that had wandered too near the young system. Once expelled, the mathematics suggested, such a world would simply continue. It would carry its momentum outward into the darkness, and there would be no force to bring it back. Think about this for a moment. The mathematics of orbital mechanics, those elegant formulas that describe how bodies move through space under gravity's invisible hand, they permit this scenario. They demand it, almost. If a planet gains enough velocity during an encounter with another object, its orbit becomes hyperbolic rather than elliptical. It curves away from the star that birthed it and never returns. The numbers themselves became a kind of prophecy, a quiet mathematical whisper that suggested the galaxy must be full of such wanderers, even though no one had ever seen one. The earliest theoretical explorations of this idea began to appear in scientific literature in the middle decades of the 20th century, though they were treated with the kind of polite skepticism that new theories often receive. Were planets really being ejected from solar systems that frequently? Was such a process common enough to matter? The skepticism was reasonable, because after all, we could not see these objects. We could not point a telescope at them. They would emit no light of their own, only the faintest residual heat from their formation. Against the brightness of stars and the backdrop of countless other celestial objects, how could one ever hope to find them? Yet there was something almost beautiful about this theoretical exercise, something that called to the imagination. Here was gravity, that most fundamental force, capable of creating not just orbits and systems and cosmic order, but also this other category of existence, the unbound, the homeless, the eternally drifting. The mathematics suggested that once a planet was ejected, it would continue in its trajectory through space essentially forever, or at least until it encountered another massive object with enough gravitational force to capture it again, which, given the vast distances between stars, would be extraordinarily rare. The early theoretical work focused on understanding the mechanisms. How exactly would such an ejection occur? In a young stellar system, before the orbits had fully settled and the inner solar system had cleared of planetary embryos, there were chaotic interactions. Planetary bodies, still forming and growing, would collide and scatter. A body forming far from its star might be perturbed by a neighboring planet into a slightly wider orbit. Another collision could increase the perturbation. Over thousands or millions of years, these gentle nudges could accumulate until a world was pulled so far from its sun that the sun's gravity could no longer hold it. At some critical moment, the ejection would become final. Or consider this alternative pathway that also emerged from the theoretical literature. A star passing through a young stellar cluster, and the early universe, billions of years ago, was full of dense stellar nurseries where many young stars clustered together. That passing star could swing close to a forming planetary system. Its gravity would tug at the planets, and if the encounter occurred at just the right angle and distance, one world could be torn away entirely, sent careening off into space, while the system it left behind continued to orbit their own star, still bound but fundamentally altered. As these theoretical ideas developed, they became increasingly refined. Scientists began calculating probabilities, examining the conditions under which such ejections would be most likely to occur. Massive planets were more easily ejected from young systems than smaller ones, the mathematics showed. Planets in the outer reaches of a system were vulnerable. Planets in crowded systems, systems with many bodies interacting gravitationally, were particularly prone to being scattered. The farther from the sun you looked, the more likely you were to find worlds on the verge of independence or already liberated from it. What made these predictions so compelling was their universality. If these mechanisms were real, and the mathematics strongly suggested they were, then not just our solar system, but essentially every solar system might be producing rogue planets. The process would not be rare or anomalous. It would be a normal, perhaps inevitable, part of how planetary systems evolved. Some systems might produce one or two rogue planets during their chaotic youth. Others, more crowded or more prone to close encounters, might produce many. But it seemed certain that wherever stars formed from collapsing clouds of gas and dust, wherever planets coalesced around those infant stars, some of those planets would eventually be ejected. This realization, which began as mere theoretical speculation, carried with it an unsettling implication for how we viewed the cosmos. The universe, it seemed, was not orderly in the way we had sometimes imagined. A tidy arrangement of stars, each with their own planetary system orbiting peacefully around them. Instead, there was a kind of violence baked into the very process of planetary formation. There was chaos, there were wanderers, there were worlds whose story did not end with eternal orbits around a nurturing sun, but rather with expulsion, with freedom, with aloneness. The mathematicians and theoretical astronomers of the 20th century were describing something that would take decades more to confirm observationally, but by proposing the mechanism, by showing that gravity permitted and even encouraged the formation of such orphaned worlds, they had already fundamentally expanded our understanding of what the universe contained. They had shown that the mathematics spoke of hidden populations, silent witnesses to cosmic events, worlds moving through the darkness that we could not yet see, but whose existence was written in the equations themselves. And there was something profoundly quiet about this knowledge. These mathematicians and their colleagues were not making sensational claims. They were not announcing that the universe was full of rogue planets, or that such objects were common. They were simply following the mathematics where it led, allowing the gravity equations to tell them what should be possible. But in doing so, they had transformed a theoretical curiosity into something more, a prediction waiting for confirmation, a whisper from the mathematics suggesting that the universe was larger and stranger and more full of solitary wanderers than anyone had previously imagined. And so we arrive at the question of beginnings. How did these solitary wanderers come to drift through the darkness, untethered and alone? The answer lies not in some distant moment of creation, but rather in the turbulent infancy of solar systems themselves, in the gravitational choreography that unfolds when multiple worlds are born too close together, in the same spinning disk of gas and dust around a newborn star. Picture, if you will, a young solar system perhaps 5 or 10 million years old. Around its central star, several planets have already coalesced from the primordial disk. They are not yet settled, they are not yet peaceful. Instead, they move in crossing orbits, their gravity tugging at one another with invisible threads, each world exerting its own pull on its siblings. This is the birthplace of chaos, and it is beautiful in its way, a time when gravitational forces have not yet achieved the quiet equilibrium they will eventually find. In some of these systems, the mathematics of gravity plays out in a way that is almost inexorable. Imagine 3 planets, or 4, orbiting too close to one another. As they complete their circuits around their star, they sometimes approach more closely than at other times, and in these moments of near approach, their gravitational influence on one another becomes profound. A larger planet might tug at a smaller one, just enough to change its trajectory. That smaller world might then be sent into an orbit that brings it closer still to another sibling. And so the dance quickens. The energy that binds these worlds to their star, and to one another, is a finite thing. Over time, as planets collide gravitationally, not with impact, but through the invisible forces that govern their motion, some of that energy must be shed. It is like a pendulum that swings less widely with each pass, gradually settling into a smaller arc. Except in this case, the loss of energy has a profound consequence. For a planet caught in an unfavorable trajectory, losing energy in a gravitational encounter with a more massive sibling means falling inward toward the star. But not always. Sometimes, paradoxically, a collision in the gravitational sense can give a small world a boost, accelerating it so violently that it is flung outward with tremendous speed. This is the mechanism of ejection, and it happens, according to our mathematical models and our observations of distant young systems, far more often than we might initially suppose. A newly formed planet, perhaps one that formed farther out in the disk, or one that was always somewhat unlucky in its position, encounters a much larger world. The encounter is brutal in its way, though we must remember that no physical collision occurs, only the invisible tug of gravity. In the moments of their closest approach, the larger world accelerates the smaller one, bending its path, transferring its momentum, and then, as quickly as the encounter began, it is over. The smaller planet hurtles outward, its velocity now far too great to be held by the star's gravity. It has been cast free. What is remarkable is that this process is not a rare catastrophe. Rather, it appears to be a natural consequence of how planetary systems form and evolve. When multiple planets form in the same disk, around the same young star, their orbits are not pre-assigned. The disk itself is dynamic, churning, settling. Planets migrate inward and outward as they interact with the remaining gas. They collide with one another, sometimes merging, sometimes scattering. And in many systems, the outcome of this gravitational dance is that one or more planets are expelled entirely. Think of it as a settling, much like what happens in a home after a long, chaotic evening. Picture a house full of guests, the noise and activity reaching a peak. Everyone is moving about. Conversations overlap. The energy is kinetic and electric. But as the evening deepens and the hours grow late, something shifts. Gradually, the disorder arranges itself. Some guests depart. Those remaining find their natural places. The noise softens. The movement slows. Eventually, a quiet equilibrium is achieved. The house settles. This is what happens in a young solar system, though the timescales are vastly longer and the forces are unimaginably greater. A young system begins in a state of ferment. Its planets are still arranging themselves, still discovering their preferred orbits, still interacting with the leftover dust and gas and with one another. There is tremendous energy and motion, but slowly, over millions of years, the system finds its balance. Some worlds remain, held in stable orbits around their star. Others are scattered, flung into paths that take them away from their sun forever. The system, like the quieting house, achieves a state of relative peace. And what of those ejected worlds? They do not simply vanish into the void. They continue on, their momentum carrying them outward and onward. They leave behind the gravitational well of their birth star, the heat and light they once orbited. They enter the cold, dark spaces between stars, and there, in those vast and silent regions, they drift alone. The solar system that ejected them may look upon them no more. The star that once illuminated them fades to invisibility, becoming merely another point of light among billions. And these worlds become what we call rogue planets, the refugees of young stellar systems, the castaways of gravitational chaos. The number of these ejected worlds is almost certainly far greater than the number of planets that remain bound to stars. For every world like our Earth, quietly orbiting its sun, there may be several others that have been cast adrift. This is not a failure of creation, but rather a natural outcome of how planetary systems are born and how gravity works its effects across the cosmic distance. The universe is far more full of wanderers than we once imagined, far more populated with solitary worlds than with those that remain close to home. And so we understand that rogue planets are not mysterious accidents, not rare and inexplicable anomalies. They are, instead, the inevitable result of the process by which stars collect planets in their infancy. They are the natural outcome of gravitational dynamics playing out as they must. And in this understanding, there is something strangely comforting. These lonely worlds are not orphans in the sense of being unwanted or rejected. They are, rather, the products of a process as old as stars themselves, as fundamental as the laws of gravity that govern all motion in the universe. But there exists another pathway to planetary solitude, one that requires no violent expulsion, no gravitational wrestling match between siblings competing for orbital space. Some rogue planets, it appears, are simply born free. They emerge not from the chaos of a crowded nursery, but from the quiet collapse of isolated clouds so sparse, so distant from any forming star, that they never experience the pull of stellar gravity at all. They condense and cool into worlds while drift alone, their genesis a story of gentle accumulation rather than desperate flight. Deep within the cold reaches of molecular clouds, those vast, diffuse regions where stars themselves are still gathering their first wisps of matter, something different unfolds. Picture, if you will, a corner of space where the density of gas and dust remains just sufficient to allow gravity to work its slow, patient mathematics, yet insufficient to kindle the thermonuclear forge of a star. Here, in these quieter pockets, small clumps of material can still aggregate. They pull other particles toward them through their own modest gravitational embrace. Dust grains collide and stick. Molecules cling together. The accumulation is gradual, unhurried, almost imperceptible on human timescales. But over millions of years, a breath in cosmic terms, something takes shape that was not there before. What makes this birth story fundamentally different is the absence of a parent star's influence. In a typical star-forming region, a massive cloud collapses under its own weight, and from that collapse emerges both a bright central star and, circling it eventually, the planets. The newborn star's gravity structures everything around it. Its radiation warms the surrounding disk of gas and dust. Its presence defines the entire system's future. But in these isolated pockets, there is no such central anchor. The forming planet grows without tutelage, without the organizing principle of a massive stellar companion. It simply becomes. The mathematics governing such a scenario remains elegant and somewhat mysterious. Astronomers calculate that Jupiter-sized worlds require an enormous mass of material to coalesce. Roughly 300 Earth masses of gas and rock must accumulate together, and the timescales involved are substantial. Without the assistance of a star's gravity to accelerate the process, or the dynamical stirring that multiple planets provide to one another, the question arises, can such massive planets realistically form in isolation? It is here that theoretical models become gentler, more speculative. Some simulations suggest that yes, under the right conditions, a particularly dense knot of gas, a favorable temperature gradient, perhaps a triggering collision between larger clumps, a planetary embryo can grow and persist. Others propose slightly different mechanisms. Perhaps these isolated objects form more readily at lower masses, as sub-Jupiter or Neptune-like worlds, though the distinction between a very massive planet and a brown dwarf begins to blur at these scales, and the naming becomes almost philosophical. What captivates many researchers is that this process, if it occurs, creates planets that are born into absolute darkness and cold. Unlike their ejected cousins, who at least experience the warmth of a star's presence during their earliest moments, planets forming in isolation from truly orphaned gas clouds begin their existence in profound chill. They condense and gather in an environment where the nearest star might be light years away. a mere point of light among countless others, offering no significant warmth or influence. The growing planet accretes material drawn from a halo of dust and gas that extends around it. Yet this material is so diffuse, so spread across such vast distances, that the process feels almost leisurely. There is no race, no competition, no urgency imposed by stellar radiation or the gravity of nearby siblings. The distinction between these solitary formed worlds and ejected planets carries subtle implications for their internal structure and composition. An ejected planet, having been baked in proximity to a star before its expulsion, might retain certain chemical imprints of that earlier epoch, a particular distribution of volatile compounds perhaps, or a core warmed and differentiated by the star's radiation. A planet born in isolation, conversely, would accrete its material from the cold, primordial mix of the isolated cloud itself, undifferentiated by stellar processing. Whether this leads to meaningful differences in their interiors remains an open question, though it intrigues planetary scientists who wonder whether a wanderer's thermal and compositional history might somehow hint at its birthplace. One might wonder, if such planets form in such quiet obscurity, how would they ever be detected? They emit no light save the faint infrared glow of their own residual heat from formation, and that heat, too, dims with each passing million years. They orbit no star whose light might be blocked by their passage. They move through the galaxy untethered and unsignaled, as if the universe itself conspired to keep them hidden. Yet detection, as shall be explored in later moments, has proven possible through remarkably clever optical techniques that make use of distant starlight and the subtle bending that a passing rogue planet's gravity can induce. For now, it is enough to sit with the notion that somewhere in the darkness between stars, in those sparse and solitary clouds where the density barely permits gravity's work, worlds may be quietly assembling themselves. They condense from the cold, accrete the drifting material around them, and eventually, when enough mass has gathered, they slip into their own permanent wandering. They are born into solitude but not into emptiness. The cosmos around them pulses with distant radiation, with the gentle tug of far-off stars, with the vast unfolding of gravitational geometry on scales almost too large to fathom, and yet each one drifts alone, a world that has never known orbit, never known the rhythmic return to the same point in space. That, too, is a form of freedom. Now, imagine standing on the surface of one of these wanderers, your boots touching stone and ice that have known no sun's direct warmth for millions upon millions of years. The sky above is absolute black, not the deep blue-black of a moonless night on Earth, but true emptiness. And yet, this world is not entirely cold. This is perhaps one of the most surprising truths about rogue planets, and it lies in a principle so fundamental that it shapes everything you see and feel around you, even now in the stillness of your room. You see, when a star dies, or when a planet is cast adrift from its solar system, it does not simply stop being warm. Heat does not vanish. It transforms. It radiates outward, but most importantly, it lingers. Deep within the crust and mantle of a rogue planet, far beneath the frozen surface where no photon from a distant star will ever penetrate, there exists a slow, patient ember, and this ember comes from many sources. The first source is gravitational compression itself. When a world forms, whether it is torn from a young solar system by the violent dance of planetary siblings, or whether it coalesces alone in the cold cloud of gas and dust from which it arose, the very act of gathering all that material together releases tremendous energy. Imagine countless fragments falling inward, colliding, converting their motion into heat. This is called accretional heating, and for a newly formed rogue planet, perhaps a few million years old, this warmth can still be profound, still radiating through the thin crust in the form of volcanic activity, in the slow convection of molten layers, in the subtle emanations that, if anyone were standing there to measure them, would register as a faint glow in infrared light. But there is another, deeper source of heat that persists far longer, a source that will continue warming these solitary worlds for billions of years to come. It is radioactivity. Within the rocky interior of a rogue planet, certain elements, uranium, thorium, potassium, continue their ancient process of nuclear decay, slowly transforming into lighter elements, releasing energy as they do. This is not a rapid process. It is glacially slow, but it is relentless, and it occurs in every rogue planet just as it does in the Earth beneath your feet. The difference is that on Earth, much of this heat energy is carried away by the warmth of the sun during the day, balanced by radiation back into space at night. On a rogue planet, there is no such balance. There is only outward radiation into the infinite void. So a rogue planet, in its first few 100 million years, may retain considerable internal heat. Its interior may be molten or semi-molten. There may be convection currents within the mantle, slow rivers of hot rock circulating from the core outward toward the surface. And where this heated material reaches the surface, volcanic activity may occur, geysers of molten material erupting into the darkness, liberating gases, briefly illuminating a few square kilometers of frozen landscape before cooling and settling back into silence. These volcanoes would produce no sound that human ears could hear, for there is no air to carry vibrations. But they would shine, faintly, in the infrared spectrum, a whisper of brightness against the absolute black. As time passes, and here we are speaking of millions of years, then tens of millions, then hundreds of millions, this internal warmth gradually radiates away into space. The rate of this loss depends on the planet's size, its composition, its internal structure. A larger world radiates its heat more slowly than a smaller one, because it has more material to cool, and because surface area increases more slowly than volume. A world with a thick, insulating mantle of rock will cool more slowly than one with a thin crust. And so a rogue planet that is perhaps 10 times the mass of Jupiter might retain usable internal heat for many billions of years, longer than the current age of the universe, in fact. But what does this residual heat mean, practically, for a world drifting alone in the dark? It means that the surface, though never touched by sunlight, is not uniformly frigid throughout its history. Picture the planet in its youth. The surface temperature might be maintained at a few hundred degrees Kelvin in some regions, warm enough that water, if present, might be liquid near certain volcanic vents or thin-crusted regions. Picture this same planet, now 5 billion years old. The surface has cooled dramatically, perhaps to only a few dozen degrees above absolute zero. The internal heat continues to radiate, but more slowly, more subtly. What is remarkable is that despite this cooling, the interior never quite reaches equilibrium with the void. There is always a temperature gradient, warmer deep within, cooler at the surface. This gradient persists, not because new energy is being added, but because heat flows outward so incredibly slowly through rock and ice that it takes incomprehensible lengths of time for the interior to equilibrate with the frozen exterior. A rogue planet may still be cooling, billions of years after its formation, radiating away the captured heat of its own creation, like a sleeping animal slowly losing warmth beneath a blanket on a cold night. And this is where the poetry begins to arrive, where physics touches something almost philosophical. A rogue planet is not a dead world, even in its advanced age. It is a sleeping world, still warm at its heart, still slowly sharing that warmth with the void around it. The energy it radiates is minuscule compared to the energy of a star. A rogue planet might shine with the faint glow of a dying coal compared to the sun's brilliant flame, but it is there. It persists, and if anyone possessed instruments sensitive enough to detect the infrared light it emits, they could read the story of that planet's age in the temperature of that glow. Have you ever considered that the oldest, coldest, loneliest objects in the universe are still, in their own way, alive? They are still changing, still radiating, still participating, however quietly, in the grand choreography of thermodynamics that governs all matter and energy. A rogue planet, drifting alone through the dark, is not a monument to death. It is a monument to the slow persistence of heat itself, to energy that refuses to dissipate all at once, but instead leaks away across eons, leaving the world subtly, perpetually warm at its core, even as its surface has forgotten the touch of any star. And so, as you imagine standing on that frozen ground, you might now picture the faint rumble of heat far below, the imperceptible vibrations of convection currents within the mantle, the radioactive decay continuing its patient work in the depths. This world is older than you can truly comprehend, and yet it is still warm inside. It is still, in its own slow way, alive. Now imagine this problem. You are an astronomer who desperately wants to find something you cannot see, something that produces no light of its own, something that refuses to announce itself through any wavelength of radiation your telescopes can detect. How would you even begin to look for an object that, by definition, hides in absolute darkness? The answer is both elegant and deeply patient. It relies on one of the universe's most subtle tricks, the way gravity bends light itself. This is where microlensing enters the story, like a whisper that arrives only if you are standing very still in the right place at the right time. The principle behind it is deceptively simple, though its application requires telescopes of remarkable sensitivity and minds willing to wait through years of patient observation, scanning the same patch of sky night after night. What microlensing does is turn an invisible rogue planet into a temporary lens, a gravitational magnifying glass that bends and distorts the light from a distant star in a way that becomes detectable to us, even though we never see the planet itself. Think of it this way. Imagine looking out at a night sky, and somewhere in the depths of that darkness, a rogue planet drifts silently between you and a distant star. That star is so far away that its light has been traveling through the vacuum of space for years or decades to reach Earth. The star is not aware of the rogue planet lurking in front of it. It simply emits its steady glow, that ancient light continuing its long journey across the dark. And then something remarkable happens in that moment, when the rogue planet passes into alignment with our position and that distant star. The gravity of the rogue planet, that lonely, invisible world, warps space around itself. And space, you see, is not truly empty. Space is the medium through which light travels. When gravity curves space, it curves the path of light as well. The starlight bends around the rogue planet's gravitational well, the way light bends when it passes through the curved lens of a telescope or eyeglass. This bending can cause the star's light to appear brighter, even slightly magnified. The star, from our vantage point here on Earth, seems to flare. Its brightness increases, and then, as the rogue planet continues its silent drift and the alignment shifts, the magnification fades away. The star dims again. The whole event lasts only a few hours, sometimes just a handful of days. But in those fleeting moments, the rogue planet announces itself through the very light it is bending. The technique is called gravitational microlensing because the effect mimics what a simple lens does to light, and because the magnification is typically small, a few times brighter than the star's ordinary glow, not a dramatic transformation. And yet this subtlety is precisely what makes it so powerful as a detection method. It requires no light from the rogue planet. It asks nothing of the wandering world but to pass in front of a background star at just the right moment. It is a technique born of patience and mathematics, of understanding how gravity speaks through the language of light. What makes microlensing especially beautiful for finding these invisible travelers is that it is entirely geometry dependent, and therefore nearly democratic. A rogue planet of any mass, moving through any part of space, can theoretically cause a microlensing event if the geometry aligns correctly. Unlike many other astronomical techniques that favor certain types of objects over others, microlensing cares not whether the rogue planet is the size of Neptune or as small as Earth. It does not matter whether the planet was ejected from a solar system or formed alone in a cloud of gas. If it drifts between us and a star, and if the gravity is just right, the light will bend and we will see it. The challenge, of course, is that this alignment is extraordinarily rare. The stars are vast distances apart. The rogue planets are tiny compared to that immensity. The odds of a perfect alignment in any given observation are vanishingly small. This is why astronomers do not search for individual microlensing events by looking at random patches of sky. Instead, they point their telescopes at the most crowded star fields they can find, toward the center of our galaxy, where stars are packed so densely that the probability of alignments increases. They observe the same region night after night, month after month, sometimes for years. They measure the brightness of countless stars with exquisite precision, and sometimes, in that data, a star's brightness unexpectedly rises and falls in a pattern that cannot be explained by any ordinary stellar variation. Consider what astronomers must do once they notice this telltale brightening. They must confirm that what they are seeing is not a background supernova, not an eclipsing binary star, not some other astronomical phenomenon that naturally causes brightness changes. They must measure the light curve, the precise graph of how brightness changed over time, and compare it to the theoretical predictions of what a microlensing event should look like. The shape of this curve carries information. The duration of the event hints at the mass of the rogue planet. The amount of magnification suggests its distance from us. Specialized software analyzes the light curve and can even estimate the planet's mass with surprising accuracy. What is truly remarkable is how much information can be extracted from photons, from light, when that light has been bent by a gravity field you cannot see. There is something almost meditative about this process. An astronomer sits with measurements from observations made across weeks or months, watching a star's light curve emerge from data, slowly realizing that an invisible world has just made itself known, not through its own emission, but through its graceful manipulation of light from another star. The technique is so elegant, partly because it requires no special alignment of equipment. The telescopes used for microlensing surveys are often survey instruments, wide-field cameras that can watch thousands of stars in a single frame. They do not need to be the most powerful instruments in the world. They simply need to be reliable, consistent, and patient. They gather their data, night after night, across seasons and years, and in that patient accumulation of measurements lies the capacity to reveal these hidden worlds. There is something almost peaceful about the microlensing method when you consider it this way. The way it asks astronomers to engage in a kind of cosmic listening, watching for moments when gravity and geometry align to send a subtle signal across the darkness. It is not a search that relies on drama or sudden revelation. It is quiet. It is meditative. It is the kind of detection that rewards those who know how to sit with data and listen to what the universe is telling them through its most delicate mechanisms. For decades, the search remained theoretical. Astronomers could imagine these wanderers, could calculate their probable existence through the mathematics of gravity and chaos. Yet no confirmed rogue planet had ever actually been seen. The universe kept its secret. And then, in the 1990s, something changed. A patient project called OGLE began its work, the Optical Gravitational Lensing Experiment. A series of telescopes spread across the southern hemisphere, watching millions of stars night after night with an almost meditative persistence. The astronomers behind it were looking for dark matter, for the invisible scaffolding holding galaxies together, but their instruments were simultaneously catching something else. Every so often, as a rogue planet drifted in front of a distant star, its gravity would bend the starlight like a lens, and for a few precious hours, that distant star would brighten and fade in a distinctive pattern. These microlensing events were rare and fleeting, but Ogle's patient vigilance meant it could catch them. By the early 2000s, as Ogle's data accumulated year by year, something remarkable emerged from the numbers. When astronomers looked at the frequency of these microlensing signatures and tried to work backward to understand what was causing them, they began to realize something unsettling and magnificent at once. It appeared that rogue planets, worlds without stars, might not be rare outliers at all. The mathematics suggested there could be more of them drifting through the galaxy than there were stars burning in the sky. The numbers whispered it first, softly, almost uncertainly. Could our cosmic understanding be so fundamentally incomplete? Could we have been walking through a city of invisible wanderers all this time? As the 2000s progressed, other surveys joined in the patient watching. The Japanese project MOA, the Microlensing Observations in Astrophysics Group, added its own telescopes and its own careful observations, corroborating Ogle's hints with independent data. The picture began to grow steadier, more convincing, though still composed almost entirely of statistical inference. No one was seeing these planets directly, they remained invisible, but the gravitational signatures they left behind, the gentle lensing of starlight, built up a slowly accumulating catalogue of the invisible. It was like learning to read the footprints of animals you could never quite see, and realizing from the patterns that the forest was far more crowded than anyone had imagined. And then came Kepler. Launched in 2009, the Space Telescope's primary mission was to find planets orbiting stars by watching for the tiny dips in starlight when a planet passed in front of its sun. But Kepler's extraordinarily sensitive instruments also became, incidentally, one of the most powerful tools yet for confirming microlensing events from space, where Earth's atmosphere could not blur or distort the observations. Kepler's data, combined with the patient ground-based surveys, allowed astronomers to build a more robust picture of the rogue planet population. With each new year of observation, each new published study, the estimates of rogue planet abundance grew. Not dramatically, the science advanced carefully, cautiously, but with a steady, inexorable shift in the direction of abundance. What these surveys revealed was almost quiet in its implications. For centuries, astronomers had thought of planetary systems as tethered things, orbits held in place by a star at the center like children holding hands around a maypole. But the new data suggested that the universe had a different arrangement. Perhaps half of all planets ever formed had been ejected from their birth systems, knocked loose by gravitational interactions, sent wandering. Perhaps the galaxy was not a collection of discrete, orderly solar systems at all, but something far more complex and tumultuous. A vast cloud through which countless solitary worlds drifted, freed from their original suns but still existent, still real, still substantial. The change was not in how the universe actually was. The change was in how we finally began to see it. The surveys quietly revealed another profound truth as well. The rogue planets being detected were not all the same mass or composition. Some appeared to be larger than Jupiter, gas giants that had been cast into the dark. Others seemed smaller, perhaps more similar to Earth or Neptune. This variety hinted that rogue planets formed through multiple pathways, that the universe had engineered their freedom in many different ways, in many different epochs, as long as stars had been forming and dying and creating new worlds. The The data was beginning to compose a far richer, more intricate narrative than the simple binary of stellar planets versus rogue wanderers. It was beginning to suggest that the rogue planet population was not a minor curiosity, not a few exceptional cases, but a fundamental and abundant feature of how solar systems actually behaved. And still, as we move into the observations made in the decades that followed, the rogue planets themselves remained unseen. They drifted through the darkness, invisible to direct telescopes, known only through the gentle mathematics of their gravitational effects on starlight passing near them. Yet they were no longer merely theoretical. They had entered the realm of the measured and the documented. Somewhere in the cold dark between the stars, countless worlds moved on their solitary paths, and humanity, through patient observation and careful calculation, had finally begun to prove that they were truly there. Among the first rogue planets to capture the attention of astronomers was one that carried the designation Ogle 2016 BLG 1928, a name far too technical and distant to capture what it truly represents. A solitary wanderer of profound isolation, drifting somewhere in the direction of the galactic bulge, that dense hub of stars and dust at the center of our Milky Way. The discovery itself came not through direct observation, which would have been impossible given how utterly dark and invisible such a world must be, but through that delicate technique of microlensing we touched upon before, where the planet's mass bent the light of a background star just enough, just briefly enough, for sensitive instruments to register the subtle distortion and deduce that something massive, something real, was passing in front of that distant light. What makes this particular rogue planet so compelling as a character study is not merely that it was confirmed, but what we learned about its solitary nature through careful calculation and repeated analysis. Astronomers estimated its mass to be somewhere in the range of 2 to 4 Jupiter masses, making it a gas giant cast adrift, far heavier than Earth, far more substantial than any terrestrial world, yet rendered entirely invisible to human eyes. 2 to 4 Jupiters. Pause on that thought for a moment. It suggests a body so enormous that it could contain 1,000 Earths within its cloudy atmosphere. A giant that once orbited suns or floated freely from its birth, now wandering through the depths of space with no companion, no anchor, no gravitational master calling it home. The distance to this particular world has been estimated at roughly 20,000 light-years from Earth, placing it well within the galactic bulge itself, nestled among the dense swirling populations of old stars and ancient dust clouds, where the light from countless suns mingles and overlaps. 20,000 light-years is a distance so vast that the light we see when we look in that direction has been traveling toward us since long before human civilization existed, since our own ancestors were only just beginning to walk upright across the African savanna. To reach this rogue planet in any physical sense would require a journey so long, so impossibly protracted, that no spacecraft humanity has ever built or imagined could hope to traverse it within any reasonable span of time. Yet here it drifts, indifferent to our inability to visit it, moving through space at a velocity estimated at somewhere between 10 and 30 kilometers per second, a pace that seems leisurely on human scales but represents motion across the vast cosmic distances at a speed that carries it hundreds of kilometers every single hour. What you might pause to wonder is whether this particular rogue planet, Ogle 2016 BLG 1928, ever passes through regions of the galaxy where other rogue planets drift. The vast majority of our galaxy is empty space, an unfathomable emptiness punctuated only rarely by matter, yet the rogue planets are thought to be numerous enough that chance encounters might occasionally occur. If two rogue planets were to drift near one another across the millennia, their gravity would disturb both of their trajectories slightly, bending their paths in ways that would leave invisible marks upon their futures. two wanderers meeting in the dark, changing each other's courses forever, and then drifting apart again into solitude, perhaps never to meet anything else in all their existence. The fascinating quality of this particular confirmed rogue world is how its discovery changed what we thought possible. Before microlensing revealed Ogle 2016 BLG 1928 and others like it, these objects existed in the realm of theory and mathematical prediction. They were thought to be real, yes, but they remained invisible phantoms, ideas that dwelt in the minds of theoretical astronomers but had never been directly confirmed. Once the first few were discovered through that delicate bending of starlight, it became clear that the universe had been populated all along with these solitary worlds, wandering unseen through the cosmos since the earliest days of the galaxy's formation. How many were out there? Billions, perhaps. Enough that they might outnumber the stars themselves, a hidden population moving through the darkness in perfect silence, their existence utterly unnoticed by the majority of the universe around them. There is something quietly moving about studying a single rogue planet like this. This object designated Ogle 2016 BLG 1928. This mass of gas and rocky core that has never orbited a sun, that has never felt the warmth of a star's radiation upon its atmosphere, that travels through absolute darkness across the gulfs between the arms of the galaxy. It had no name given by ancient peoples. No astronomer watched it rise in the evening sky. No poet ever wrote of its beauty, because no eye from any populated world has ever seen it. It simply exists, has always existed perhaps, drifting at its slow, steady pace, carried along by the galactic currents, unchanged and unchanging in its journey through the cosmic dark. When you consider such a world, when you imagine its slow passage through regions of space so distant from us that the light reaching us from them took longer than human civilization has existed, you begin to develop a deeper sense for how much of the universe moves beyond our knowledge, beyond our sight, beyond even our most distant instruments. These rogue planets are not anomalies or oddities in the cosmic order. They are, if current estimates hold true, the common state of existence for planetary objects throughout the galaxy. Most worlds, statistically speaking, orbit no sun. Most worlds know only darkness. And yet here on Earth, circling our humble star, we scarcely ever think of them. And yet, beneath the seeming desolation of these worlds, beneath their frozen surfaces and the crushing dark that surrounds them, there exists a possibility, remote, tantalizing, and wholly unexpected, that some of these lonely wanderers might harbor something we have long imagined only stars could nurture: warmth, and perhaps, just perhaps, liquid water. Consider this quietly. A rogue planet, cast into the void, receives no external heat from any sun. Its surface temperatures plummet to depths we struggle to fathom. Imagine a world where the thermometer does not merely drop below freezing, but falls to perhaps 50 or 100 degrees Kelvin, where the very atmosphere might crystallize and snow down to the ground as frozen gases. And yet, inside this frozen shell, hidden beneath layers of ice that might stretch for many kilometers downward, there could exist something like an ocean, not from sunlight warming the surface, but from heat rising from within the planet itself. This is where planetary geology becomes something almost like a whispered secret. Every world that forms, whether orbiting a star or drifting alone, contains within it the remnants of its birth, radioactive elements, principally uranium, thorium, and potassium, locked into the planet's rocky interior. These elements decay slowly, invisibly, over billions of years, releasing heat as they transform into lighter elements. It is a process so gentle, so patient, that we barely notice it on Earth where the sun's warmth overwhelms it entirely. But on a rogue planet, in that perpetual darkness, this internal radioactivity becomes something like a hidden fire, a slow-burning hearth in the depths of the world. How long might such heat persist? That is one of the profound questions scientists turn over in their minds. A large rogue planet, massive enough to retain significant gravity and structure, could hold on to this radioactive warmth for 10 billion years or longer. 10 billion years of quiet, steady heat, enough to melt ice and keep liquid water circulating in the caverns and channels beneath the frozen crust. One can imagine, with great tentative wonder, reservoirs of water moving slowly through rocky passages deep underground, warmed by this internal furnace, entirely shielded from the freezing void above. Now, the question that science approaches with necessary caution: could such a place be inhabited? Could life, in some form, emerge and persist in such an environment? This is where we must step carefully, for we are moving from the observed into the speculative. We know that on Earth, deep beneath the ocean floor, in absolute darkness near hydrothermal vents where superheated, mineral-rich water rises from the planet's interior, entire ecosystems thrive. Microbes, strange and resilient, draw energy not from sunlight, but from chemical reactions, oxidation of hydrogen sulfide, iron, and other compounds. Could such life exist beneath the ice of a rogue planet? The conditions are not impossible. The elements are the same. The physics is the same. But, and this is crucial, we have no evidence that it does. We have no observed example. It remains a beautiful hypothesis, a door left slightly ajar in our understanding. What makes this possibility so affecting, so calming to contemplate, is that it fundamentally reframes our sense of what a world can be. We have grown accustomed to thinking of habitability in terms of Goldilocks zones, those narrow rings around stars where temperatures allow liquid water to exist on the surface, where starlight can fuel photosynthesis. But a rogue planet offers something different, something almost humbling in its simplicity. It suggests that wherever there is planetary matter, wherever there is gravity and geological activity and chemistry, there might be the scaffolding for life. Not necessarily life, but the possibility. Life, in this vision, becomes less dependent on cosmic luck, on being positioned perfectly relative to a star, and more dependent on something more fundamental: the presence of physical and chemical processes that can organize matter into greater complexity. The scientists who study such worlds tend to speak of them with a kind of wonder, tempered by skepticism, a balance between imagination and rigor. They do not claim to know that life exists on rogue planets. They acknowledge that we have not yet developed the instruments to peer through kilometers of ice to the ocean beneath. They recognize that the emergence of life, even with all the right chemical ingredients, remains mysterious. But they do not dismiss the idea as impossible. They understand that the universe is far larger and far more strange than our theories yet account for, and that in such vast spaces, the improbable becomes probable simply through the mathematics of scale. On a rogue planet orbiting nothing, bathed in starlight alone, with an ice shell and a deep ocean, the rhythms would be entirely internal. The tides, if they existed, would be tiny, created by the pull of perhaps a captured moon, or so faint as to be nearly unmeasurable. Time itself would move differently, not in day and night cycles driven by stellar rotation, but in the slow geology of the planet, the migration of minerals through water, the grinding and settling of rock. One might imagine, in the depths of such a world, a kind of peace found nowhere else in the cosmos, a perfect isolation, a self-sufficiency that requires nothing from beyond its boundaries to persist. Yet we must also honor the profound uncertainty that surrounds all of this. We do not know how common such conditions are among rogue planets. We do not know whether the internal heat of a world is sufficient to maintain liquid water for timescales long enough for life to emerge. We do not know what form life might take in such circumstances, or whether the chemical processes that sustain life in Earth's deep oceans would function identically in water hidden on a world utterly removed from the sun's influence. These are the kinds of questions that science holds gently, without grasping at them too firmly, waiting for better observations, finer instruments, and the slow accumulation of knowledge. For now, the rogue planets keep their secrets. They drift through the galaxy. If they possess oceans beneath their ice, those oceans remain hidden from our view, silent, patient, perhaps teeming with life, or perhaps as sterile as the vacuum that surrounds them. And there is something peaceful in that unknowing, something that invites us to sit with the mystery without demanding immediate answers. What becomes quietly stunning when astronomers began to compile their observations across decades is the sheer abundance of what they were not seeing. Each survey that searched the cosmos for these invisible wanderers, the gravitational lensing campaigns, the infrared searches, the patient catalogues of anomalies, painted a picture not of rarity, but of profound abundance, a population so vast that it fundamentally reshaped our understanding of what the galaxy actually contains. Consider for a moment that for much of human history, we measured the universe by counting stars. We could see them, they blazed, they were the architecture upon which we built our sense of cosmic order. But rogue planets exist in a different category entirely, and their numbers suggest something almost humbling about the limits of visibility itself. Current estimates, refined over the last 2 decades through careful statistical analysis and increasingly sophisticated models, propose that our galaxy alone might harbor somewhere between 50 billion and 400 billion rogue planets. The range reflects genuine scientific uncertainty, but even the lower bounds are staggering. Let that settle for a moment. Billions, perhaps as many as 400 billion individual worlds, adrift and unseen, outnumbering the approximately 200 to 400 billion stars that illuminate the Milky Way. In some models, there may be as many rogue planets as there are stars. In others, they may exceed the stellar population by a factor of 10 or more. What does this mean? It means that the universe you live in contains vast populations of worlds that are fundamentally invisible to human sight, that emit no light of their own in any wavelength we can easily detect, that exist in a state of cosmic anonymity more profound than almost any other category of celestial object. It means that as you stand beneath a night sky and count the stars, a practice that feels ancient and intimate, you are looking at perhaps only a tiny fraction of the actual worlds that drift through the space above you. The darkness between the stars contains far more than darkness. It contains wanderers. This abundance carries with it a peculiar kind of peace. When something becomes common enough, when it rises to a level of sheer statistical inevitability, it ceases to feel like an exception or an anomaly, and instead becomes part of the ordinary fabric of existence. Rogue planets are no longer curiosities discovered by chance. They are a standard feature of our galaxy, as unremarkable in their way as clouds of gas or the slow cosmic dust that drifts between suns. They are common, they are natural, they simply exist in such vast numbers that we are only now, through the patient accumulation of evidence, beginning to appreciate their presence. The models that produce these figures rest on careful logic. Astronomers observe the properties of planetary systems that we can see clearly, systems orbiting known stars, where we have measured the masses and distances and orbital mechanics with precision. From these systems, they note how many planets are ejected during the chaotic early phases of solar system formation. In young, crowded star-forming regions, gravitational interactions routinely fling young planets outward into interstellar space. The mathematics is straightforward. The percentage of ejected planets appears consistent across observations. When you apply that percentage to the total number of stars that have ever formed in the galaxy, multiplied across billions of years of stellar birth and death, you arrive at these staggering numbers. But there is also the second formation pathway, remember, the planets that never belonged to any star at all. These form directly in the cold clouds from which stars themselves condense, born in the same regions of collapsing gas and dust, but never captured by any central body. How many such worlds exist? We do not yet know with precision. Some theoretical models suggest they may be quite common, perhaps even outnumbering the ejected planets. Others propose they are rarer. This uncertainty, this honest gap in our knowledge, is itself part of the quiet beauty of the subject. We are speaking of populations that are so difficult to observe directly that reasonable estimates can still vary by orders of magnitude. The universe retains its mysteries even as we gradually illuminate them. What does this abundance suggest about the nature of planet formation itself? Perhaps it implies that the creation of worlds is a natural, almost inevitable consequence of stellar birth, a process so fundamental and so robust that planets are produced routinely, in vast numbers, far exceeding the capacity of stars to hold them all. Or perhaps it reflects something about the geometry of star-forming regions, the way gravity naturally creates instability and chaos in systems crowded with young, massive bodies. Whatever the mechanism, the result is a galaxy populated not by solitary, well-behaved systems orbiting distant suns, but by a sprawling population of independent worlds, each following its own slow path through space. This reframing of scale carries an almost meditative quality when contemplated in the quiet hours before sleep. We are accustomed to thinking of ourselves as inhabiting a relatively orderly cosmos, one organized around stars and their satellites, where most planets are bound, most futures are determined, most objects have clear relationships to one another. But the statistical reality suggested by current research is something closer to freedom and dispersal. Most planets in the galaxy may be free. Most worlds may be independent. The bound systems, the ones we observe most easily, that burn brightest, that form the backbone of our astronomical catalogues, may actually represent a minority of the planetary population, however surprising that feels. As you rest with this thought, consider what it means that the universe contains so much that remains unseen, so many wanderers moving through the dark outside the reach of our telescopes and our understanding. There is something inherently soothing about abundance, about knowing that presence does not require visibility, that existence does not demand recognition. The rogue planets drift on, whether we catalogue them or not, whether we understand them completely or hold only partial knowledge. They simply are, in their multitudes, a quiet reminder that reality always contains more than we have yet learned to perceive. Imagine, for a moment, the quietest journey you could ever conceive, not the gentle hum of an engine, not the whisper of wind through fabric, but rather the movement of something so vast and so utterly untethered that it simply drifts through the cosmic ocean with no resistance at all. This is the way of rogue planets. They move, always moving, yet in a silence so profound that even billions of years seem like a single, endless breath, and the paths they trace through our galaxy are as intricate and patient as the slow currents of a still, deep sea. A rogue planet, once ejected from its birth system or never captured in the first place, becomes subject to the grand gravitational dance of the galactic disk itself. It does not spin around some central star, following the familiar elliptical paths we know so well from our own orderly solar neighborhood. Instead, it orbits the vast center of the Milky Way galaxy itself, caught in the gentle, inexorable pull of billions of stars and untold masses of dark matter all around it. This is a motion measured not in days or months or even years, but in millions upon millions of years. A single journey around the galactic core might take 250 million years or more, and yet the rogue planet, indifferent to such timescales, simply continues, unhurried, along its slow path through the darkness. What propels it forward? The momentum it possessed at the moment of its expulsion from its home system never truly leaves it. When a young planetary system undergoes gravitational chaos, when multiple planets jostle and collide and pull at one another in the gravitational turmoil of youth, one world might find itself pushed outward with such violence that it leaves the system forever. And in leaving, it carries with it the velocity of that violent parting. This speed, which might be measured in kilometers per second in its early moments of exile, persists essentially unchanged as the world drifts outward from its sun. There is no friction in the vacuum of space, no air resistance, no force to slow it down. Once launched, it continues on its trajectory with the faithful constancy of a stone thrown into an infinite abyss. Picture a boat adrift upon a windless sea, if you will. The boat moves because it was given motion at some point in the past. The water carries it neither faster nor slower, adds no new force to its journey. It simply continues, following the gentle currents beneath its hull. So too does a rogue planet move through the galaxy. It follows the gravitational contours of the galactic structure around it, the subtle slope of the overall gravitational field created by the distribution of stars and dark matter, but in such a way that the movement appears almost timeless, almost like the stillness of drifting rather than the sensation of being carried. The galactic disk itself, that vast flattened spiral of stars and gas and dust that comprises the Milky Way, has its own slow rotation. Rogue planets, unless they happen to move in a direction aligned with this galactic spin, will drift according to their own ancient trajectories. Some of them may have originated from the outer reaches of the galaxy and now float slowly inward toward the crowded central regions. Others, born near the galactic center, may have been flung outward and now drift patiently toward the quieter, sparser outer edges where fewer stars remain. Each rogue planet, in essence, traces its own unique path through space, determined entirely by where it came from and what momentum it possessed at the moment of its liberation. Consider the sheer distances involved in these journeys. When a rogue planet drifts through the space between stars, it may encounter nothing solid for light years in any direction. The stars themselves are so far apart that even a world moving silently through the night might take hundreds of thousands of years to pass from one stellar neighborhood to another. Yet even this vast, empty expanse is not truly empty. The gravity that binds the galaxy together reaches everywhere, subtle and pervasive. Every mass in the cosmos tugs gently on every other mass. For a rogue planet, this means that while it may feel utterly alone, it is never truly free of gravitational influence. The weight of the galactic core pulls it onward. The presence of nearby stars, though separated by light years, guides its path ever so gently. It is a paradox of cosmic solitude, utterly untethered from any single sun, yet held in place by the gravity of all suns around it. The velocity of a rogue planet is, in many cases, rather modest when considered across the vast scales of interstellar space. Some rogue worlds drift at speeds of only a few kilometers per second. Others, ejected in more violent encounters, may travel faster, perhaps tens of kilometers per second. And yet even these faster wanderers move in a way that would seem frozen in time if observed from any human perspective. To cover one light-year of distance at a slow speed would take thousands of years. To traverse the diameter of the galactic disk might consume tens of millions of years. Time in this realm operates on scales so immense that they become almost metaphorical when viewed from our brief, earthbound lives. What keeps a rogue planet moving in one particular direction rather than another? It is the laws of physics, expressed in perfect, eternal equations. An object in motion, stated Newton long ago, remains in motion unless acted upon by an external force. For a rogue planet, the only external forces are gravitational, and these forces, while they curve the path of the world's journey, do not truly stop it or reverse it. The rogue planet continues forward because there is nothing to stop it. It is momentum made manifest on a scale almost too vast for the human mind to grasp. And in this endless drifting through the dark, rogue planets share a strange kind of kinship with one another. Scattered throughout the galactic disk and beyond, each isolated and untethered, they move at their own pace, following their own paths, yet all bound together by the same gravitational laws, the same cosmic architecture. Their trajectories, if plotted and traced over millions of years, would create a map of the galaxy's history, a record written not in light or visible matter, but in the slow, patient movement of worlds that refuse to belong to any sun. If you were to stand on the surface of a rogue planet, to feel its ancient, frozen crust beneath your feet, and look up at what had become its sky, you would encounter a vision of darkness unlike anything witnessed from Earth, unlike anything most humans could truly imagine without having lived there in the dark. The sun would not be there. There would be no source of heat arriving from above, no rising and setting, no day melting into dusk, no familiar arch of light painting the horizon. There would only be night, eternal and complete, and it would change everything about what you could see. Yet the sky would not be perfectly black. This is the curious, almost whispered truth that makes the rogue planet's twilight so strange and so gentle. Countless stars, each one impossibly distant, would remain visible in the thick darkness above, and because there would be no bright sun to overwhelm them, to bleach them into invisibility as it does on Earth, these distant suns would shine with a steady, patient clarity. Imagine stepping outside on the darkest night you have ever known, and then removing even that. The faintest stars you can barely see from your darkest location on Earth, the ones that seem to flicker at the very edge of perception, these would glow clearly from the surface of a rogue world. The Andromeda Galaxy might be visible as a smudged, luminous cloud, with its own delicate spiral structure resolved into individual stars. The stellar backdrop would be not sparse but genuinely rich, a depth of light that would take time to absorb, that would reward long gazing with new details, with fresh patterns emerging from the darkness. The starlight itself, though, would be so dim, so profoundly gentle, that it would struggle to illuminate the landscape beneath your feet. If that rogue planet had a rocky surface, and many probably do, that terrain would remain largely invisible, shrouded in a darkness so complete that even with perfect human eyes, you would sense the ground more through touch than through sight. You would know it was there by the solidity of it, by the subtle shifts in air temperature that might emanate from its crust, by the faint sound of wind. Yes, even rogue planets with thin atmospheres can have wind, moving across ridges and valleys you could not truly see. It would be a landscape perceived in a kind of sensory whisper rather than a clear visual statement. You might walk for hours through an alien terrain and glimpse almost nothing of its actual form. This would be disorienting, perhaps, or it might feel strangely meditative, like moving through a dream where the world exists but reveals itself only in fragments. But if that rogue planet had captured a moon, and some of them certainly have, if it had pulled a smaller world into its orbit through some ancient gravitational embrace, then that moon might become the most important feature of the night sky. Picture this: a moon orbiting your feet, a companion world glowing with reflected starlight, moving through the heavens on its own predictable path. Such a moon would not shine as Earth's moon shines, bright enough to read by, bright enough to cast a shadow. The reflected starlight striking its surface would be too faint for that. Instead, it would appear as a softly glowing pearl, a subtle presence that would mark the passage of time as it moved through its orbit, rising and setting on cycles measured not in hours as Earth's moon does, but perhaps in days or weeks, depending on the specifics of the rogue planet's gravity and the moon's distance. This gentle wanderer in the sky would become the only visible clock, the only measure of rhythm in a world that otherwise knew only the patient, unchanging darkness. There might be auroras too, though they would require certain conditions. A rogue planet with a magnetic field, with residual radiation still flowing through its interior, with perhaps an atmosphere thick enough to glow when charged particles moved through it. These theoretical auroras would be faint and rare, appearing perhaps only during particular solar wind events or cosmic ray showers, brief curtains of color that would seem almost miraculous in their rarity. What color would they be? Red, perhaps, or a very faint green, the colors that paint Earth's far northern and southern skies, but rendered in whispers, in suggestions of light rather than clear, vivid displays. For a rogue planet dweller, an aurora sighting would be an event worth remembering, a night when the darkness itself would become slightly less dark, when the universe would offer a small gift of visible beauty. The horizon, too, would hold its own subtle poetry. On Earth, the horizon marks a clear boundary between day and night, between illuminated air and darkness. On a rogue planet with little or no atmosphere, the horizon would simply be a curve, a place where the planet's curvature became apparent, marked not by a band of light, but by a faint silhouette, the solid edge of your world against the star-studded darkness beyond. If the planet had a thicker atmosphere, that horizon might glow with something like an aurora, a faint luminescence produced by cosmic rays or residual planetary heat exciting molecules in the upper atmosphere. It would be one of the few visual landmarks you could consistently locate, one of the few ways to orient yourself in the overwhelming darkness. And yet there might be a kind of peace in this, a quality of acceptance. The rogue planet's sky offers no promises of warmth, no daily reminder that the universe cares about delivering energy to its surface. It is honest in its darkness. What light exists is patient and eternal, neither growing nor fading with human-scale seasons. The stars would be older than anything on Earth, their light having traveled impossible distances to reach you, carrying stories of the distant universe in their wavelengths. To live beneath such a sky would be to accept solitude as a permanent condition, not as something temporary or regrettable, but as the fundamental nature of your world. Whether such worlds could harbor life, whether creatures could exist in the deep cold, drawing warmth from planetary interiors, building civilizations in darkness, that remains one of astronomy's most beautiful open questions. For now, that sky exists in our imagination, glowing softly with distant stars, awaiting the first moment when human instruments might look down upon it from space, revealing at last what the universe has been keeping hidden all along. And yet, as we trace these solitary wanderers through the cosmos, we find ourselves drawn to a quieter possibility still, that perhaps no rogue planet need journey entirely alone. For within the cold silence between the stars, there exists a phenomenon so delicate, so rarely glimpsed, that astronomers have only begun to catalogue its occurrence in recent years. Rogue planets accompanied by their own moons, or even more intriguingly, rogue moons themselves adrift without any parent world. These miniature systems, complete unto themselves, drift through the darkness as whole ecosystems of gravity, bound together by nothing but the mutual pull between a world and its satellite, untethered from any star's influence. Consider for a moment how such a pairing might have come to exist. When a young planetary system convulses and tears itself apart through gravitational chaos, when a wayward giant planet collides with its siblings and all are scattered like marbles across an expanding void, what becomes of the smaller bodies? The moons orbiting these ejected worlds do not simply vanish. Instead, if they possess sufficient speed and position at the moment of expulsion, they remain bound to their planetary masters through the elegant invisible thread of mutual gravity. A moon, that had spent millions of years circling its planet in a young and stable solar system finds itself suddenly orphaned of the sun, yet still held in orbit by the world beneath it. And so the pair continues onward together, planet and moon, a miniature binary system no larger than could fit within the orbit of a gas giant, yet complete in itself. The mathematics of such partnerships is remarkably stable, which might surprise you. Two bodies bound by gravity alone, orbiting around their shared center of mass, ask nothing of any distant star. They require no external anchor, no orbital highway maintained by a sun's persistent pull. Instead, they become a closed system, a kind of cosmic microcosm, where the dance between world and moon plays out in its simplest, purest form. The planet, perhaps warmed still by its own internal heat, provides whatever light and gravitational shelter its moon receives. The moon, in turn, exerts its own gentle tug, creating tides, though whether upon solid rock or hypothetical oceans remains a beautiful unknown, and serving as a companion in the endless night. But here emerges an even more speculative possibility, one that astronomers whisper about with appropriate caution in their quiet research hours: rogue moons unbound from any planet at all. These would be orphaned satellites, torn away from their parent worlds during the violent scattering events that populate interstellar space with rogue planets in the first place. A moon, ejected from its orbit with sufficient velocity, becomes not a moon any longer, but a small world unto itself. Yet it retains its essential character, perhaps smaller than a planet, perhaps composed of the lighter materials that formed in the outer reaches of a solar system. It drifts alone, a solitary marble of rock and ice rolling through the black. The formation of rogue moons poses a particular puzzle. During the early chaos of a young solar system, the gravitational interactions are violent and unpredictable. A small moon orbiting a planet that itself is being ejected might be flung clear entirely, its connection to its parent severed in the span of mere moments. Or, even more fascinatingly, a rogue moon might form not through ejection, but through capture during a brief gravitational encounter. Imagine two rogue planets passing one another in the darkness, not colliding, but coming close enough that their gravity wells overlap. A small body of rock and ice, previously independent, might become briefly ensnared in this encounter, drawn into orbit around one of the passing worlds for a few orbits, before being released once more into solitude. Such encounters must be vanishingly rare, yet in a galaxy containing billions of rogue worlds, the truly improbable becomes merely unusual. What truly captivates the mind is the contemplation of rogue systems of multiple satellites, rogue planets, accompanied by 2, 3, or even more moons. Such configurations are not implausible. When a planetary system is disrupted, why would a world lose all its moons and retain none? It seems equally plausible that some rogue planets might wander through the void, accompanied by small entourages of attendant bodies. Picture such a system, a dim world, perhaps barely warmer than its surroundings, encircled by 2 or 3 smaller moons. These satellites, visible only against the faintest backdrop of distant starlight, would trace slow arcs across the sky above the world's surface, falling and rising in a rhythm determined entirely by the gravity of their parent planet. For any observer on that world, though none has ever existed, save perhaps in the realm of hypothetical speculation, the view would be of companions, of a structured realm of motion within the vast stillness. The stability of such miniature systems is worth noting, because they exist in the vacuum of space, freed from the chaotic perturbations that would arise from a nearby star. They can maintain remarkably regular orbits over enormous spans of time. A moon orbiting a rogue planet experiences none of the gravitational interference that complicates the orbits of Earth's own moon, with its slow recession from our planet and its complex dance with the sun. Instead, the rogue moon's orbit settles into patterns that might persist unchanged for billions of years, its distance from its parent world remaining constant unless some catastrophic collision or extraordinarily close encounter with another rogue body intervenes, events so rare as to be, for practical purposes, impossible. How might an astronomer detect such a system? This is where the challenge deepens considerably. A rogue planet with its moon is already difficult to find, requiring the subtle distortion of starlight or the precise gravitational effects it exerts upon a background star during a microlensing event. Adding a moon to that rogue planet makes the detection even more delicate. A small moon orbiting a small rogue world, invisible to direct observation, produces minute variations in the planet's trajectory that require extraordinary precision to measure. Yet future telescopes, with their ever-improving sensitivity and resolution, may reveal such systems. When they do, we will finally gain a concrete accounting of how common such companionship is among the galaxy's wandering worlds. And so we arrive at the threshold of what comes next, where humanity's instruments grow quieter yet more sensitive, reaching into the dark with patient hands. For decades, astronomers could only theorize about these wandering worlds, could only calculate their existence from mathematics and gravitational whispers. But in the early years of the 21st century, a shift began to emerge, a slow recognition that to truly understand rogue planets, we would need to look harder, build better, and turn our gaze upward with instruments designed specifically for this invisible census. The Roman Space Telescope, named for the pioneering astronomer Nancy Grace Roman, represents one of the most ambitious attempts yet to catalogue the rogue population that drifts through our galactic neighborhood. Still in development, still being assembled in laboratories where patience and precision meet, this observatory will carry within it a sensitivity to the faintest traces of gravitational lensing events. Where earlier surveys had to wait for rare alignments, had to count on fortune and perfect timing, Roman will search systematically. Its infrared sensors will observe millions of stars simultaneously, watching the subtle brightening that occurs when a rogue planet's gravity bends the light from a distant star, those fleeting moments of amplification that last only hours, sometimes minutes, that would be invisible to older telescopes but unmissable to Roman's carefully calibrated eye. Think of it as humanity learning to read a new language written in curves of light. Each microlensing event that Roman detects becomes a sentence in a growing story about what truly inhabits the spaces between our familiar stars, and the predictions, based on the patterns that current surveys have already begun to reveal, suggest that Roman alone might discover thousands of these previously hidden worlds. Not in a single night, but over the course of its mission, building up a catalogue so extensive that our understanding of planetary architecture, of how worlds are born and distributed throughout space, will be fundamentally transformed. But Roman is not alone in this endeavor. There exists a quiet international effort, a collaboration of astronomers and engineers who recognize that to map the hidden populations of the galaxy requires multiple approaches, multiple instruments pointing upward from different vantage points. Ground-based observatories, those patient witnesses to the night sky, continue to refine their microlensing techniques. Networks of telescopes spread across continents now share data in real time, alerting each other when a potential event flares into view, allowing simultaneous observations that can extract far more information from a single brightening than any one telescope could alone. There is something deeply human about this coordinated watching, this shared attention turned toward the invisible. The future surveys, those that will be conducted in the years and decades ahead, will employ a kind of triangulation, not just of light, but of methods. Where microlensing excels at finding planets at certain distances, with certain masses, other techniques fill in the gaps. direct imaging, where advanced optics might actually photograph the faint infrared glow of a young rogue world, will capture worlds still warm from their violent births. Astrometry, the precise measurement of stellar positions and movements, will help identify systems where the gravitational tug of hidden companions suggests rogue planets drifting nearby. Each approach illuminates a different corner of this vast dark room, and together they begin to sketch the outline of something profound. There is a quiet confidence building among those who study these worlds, a sense that within your lifetime, within the next 15 or 20 years, we will have moved from wondering whether rogue planets are common to knowing exactly how common they truly are. The estimates have already shifted dramatically. Where once astronomers might have suggested that perhaps for every star there existed one or two rogue planets, current thinking leans towards something far more abundant. Some models propose that the number of free-floating worlds might exceed the number of stars by an order of magnitude or more. But these are still whispers from incomplete surveys, extrapolations drawn from limited data. What Roman and its successor telescopes will do is transform whispers into something more solid, more certain. And in the quiet space between prediction and discovery lies something worth contemplating. For centuries we mapped the cosmos by finding what shone, by seeking out the bright points of light and the objects that orbited them. The idea that the galaxy might be populated by countless worlds moving through the darkness unobserved, unaccounted for, seems almost to shift the very definition of what is known. How many places might exist in the universe that we have never seen and perhaps never will see? How many stories are being written in the dark, invisible to our telescopes, unfolding in the cold between the stars? The Roman Space Telescope, assuming its launch and deployment proceed as planned, will begin its work not with a great and obvious discovery, but with the patient accumulation of data. Night after night of observation, the infrared sensors gathering light that has traveled across incomprehensible distances, looking for the characteristic signature of a rogue world's gravity bending and amplifying the light of a background star. Each detection will be subtle, each one requiring careful analysis to confirm, to measure the planet's mass and distance and trajectory. But from these individual events, a pattern will emerge. A map will slowly be drawn. The hidden population will become less hidden. This is, perhaps, one of the most profound shifts in how we understand the universe. Not a single dramatic discovery, but the systematic realization that the cosmos contains far more than we ever supposed. The rogue planets, those silent wanderers that drift through the night, unmade by any star, are not rare exceptions or curiosities. They are part of the fundamental architecture of how galaxies are built. And in the coming years, as our instruments grow more sensitive and our methods more refined, we will finally begin to see them not as theoretical possibilities, but as genuine members of the cosmic community, as real and as numerous as the stars themselves. There is a particular kind of freedom that exists in the absence of obligation, and perhaps no object in the universe understands this more intimately than a rogue planet, drifting through the dark with no parent star demanding its orbit, no gravitational anchor holding it in a predictable, circular path. To exist without being bound to something larger than oneself, this is the condition of a rogue world, and yet it is not, scientists have come to realize, a tragedy. It is simply a different way of being. We tend to imagine solitude as something inherently sorrowful. Our cultures, our stories, the long history of human meaning-making, all of these have taught us that to be alone is to be diminished. To belong to something is to have purpose. To orbit something greater is to have significance. A planet around a star participates in a grand celestial dance. It catches light. It receives energy. It is, in a sense, noticed. But what becomes of a world that orbits nothing? What meaning can it hold? The answer, whispered through centuries of astronomy and philosophy alike, is this: meaning does not require an external witness. A rogue planet does not need a star to validate its existence. It does not need to shine in reflected light to be real. It moves through the cosmos with a quiet kind of integrity, following the slow geometry of gravity through the galactic plane, indifferent to whether any eye falls upon it. And there is, in this indifference, a kind of peace. Consider the human parallel for a moment, not as a direct comparison, but as a mirror held up to something we feel but rarely name. We live in an age of tremendous connectivity, and yet many people experience a deep loneliness, a sense that to matter, one must be seen, must be valued by systems larger than oneself. To be liked is to exist. To be wanted is to have purpose. We orbit the judgments of others the way planets orbit stars, our trajectories shaped by the gravity of expectation and approval. What would it mean, then, to drift free from that orbit? What would it feel like to move through the world untethered from the need to be gravitationally bound to someone else's gravity well? A rogue planet teaches us, in its silent way, that such freedom is possible. It teaches us that a world can be complete in itself, that its reality does not depend on its proximity to a greater source of light or warmth. The rogue world does not orbit. It does not perform. It simply is, traveling through the emptiness with a kind of solitary grace. This is not to suggest, of course, that rogue planets are happy or that they experience their isolation as liberation. A rogue planet knows nothing of happiness or sadness. It is not conscious. It does not yearn, but the image of it, a world moving alone through the dark, following laws of physics that care nothing for human notions of belonging. This image can offer us something. It can offer us a reframing, a way of thinking about solitude not as absence, but as a different form of presence. A way of understanding that to be unattached is not necessarily to be lost. There is, too, something almost generous in the way rogue planets move through space. They are not selfish with their existence. They do not hoard their reality or demand recognition. They simply follow their trajectories, silent and dark, asking nothing of the universe but passage. And in this asking for nothing, they give something back, a kind of teaching, available to anyone willing to listen. The teaching is simple. You are allowed to exist without justifying your existence. You are allowed to move through the world according to your own nature, following the gentle laws of your own gravity, without needing to orbit anyone or anything. Some of these rogue worlds, we suspect, may have moons, small companions that move with them through the dark. And in this possibility lies perhaps the most nuanced reflection of all. For even in solitude there can be companionship. Even in the vastness between stars there can be relationship. A rogue planet and its moon move together not because of obligation, but because of the simple, mutual gravity that holds them. They are bound and yet free. They journey together, and yet each follows its own path. This too is a kind of belonging. Not the belonging of orbiting a distant, burning star, but the belonging of moving through the darkness, alongside something else that is also moving through the darkness. What does this teach us in the quiet hours when we lie awake thinking about our own paths through the world? Perhaps it teaches us that there are many forms of connection. Not all of them are hierarchical. Not all of them require us to revolve around a larger source of light. Some of them are simply the quiet companionship of two beings moving in similar directions, held together not by duty, but by choice, or by the gentle, irresistible pull of shared existence. The rogue planet drifts on. It has drifted for billions of years, and it will continue to drift for billions more. It will never feel the warmth of a star's direct rays. It will never experience the bright, clear day, but neither will it be pulled into that sun and destroyed. It will not be consumed. It will not be used up in service to something larger. It will simply continue, moving through the cosmic dark according to the slow mathematics of gravity and motion, complete in itself, asking nothing, receiving nothing, and somehow, in that exchange of absence, existing in a state of perfect, undemanding being. And perhaps that is the deepest lesson that rogue planets offer us. Not that solitude is good, or that belonging is bad. Not that we should all strive to be independent wanderers in the dark, but rather that there is no single correct way to move through the universe. Some worlds orbit stars, some drift through the darkness, some travel with companions at their side. All of them are real. All of them are valid. All of them are allowed. As we drift further outward still, into the vast quietness that rogue planets have come to represent in our growing understanding of the cosmos, it becomes clear that these solitary wanderers are far more than astronomical curiosities to be catalogued and filed away. They are, in fact, gentle teachers of a truth that has always existed in the darkness between the stars, that the universe is far larger, far stranger, and far more populated than we once imagined, and that so much of what moves through the cosmic ocean does so in absolute silence and profound solitude, never witnessed by any eye, never circled by any observer, drifting forward through time as if through an endless night. This is perhaps the deepest lesson that rogue planets offer us as we settle into our own stillness. Consider for a moment the sheer scale of their loneliness. In our own galaxy alone, the estimates suggest billions upon billions of these worlds exist, some born into isolation, others cast out by the turbulent childhood of their solar systems, all of them traveling through the darkness on paths that will never bring them into contact with light again. And yet we know so little of them. They give us no reflected starlight to measure, no transit shadow to detect, no orbital rhythm to track. We glimpse them only rarely, through the delicate mathematics of gravitational lensing, when chance alignment allows their invisible forms to bend and magnify the light of a distant sun for just a few fleeting hours. In those brief moments, they reveal themselves like whispers, and then they slip back into the dark. This asymmetry between their abundance and our ability to perceive them speaks to something profound about the nature of existence itself. There is a kind of peace in recognizing how much of creation moves unobserved. For so long, human beings have felt compelled to catalogue, to name, to shine light upon every corner of the world around us. And yet the universe, it seems, was never waiting for our permission to exist. It has always contained these mysteries, these wandering, lightless worlds, these orphaned planets that ask nothing of anyone and require no witness to justify their being. They simply are, and have been, and will continue to be long after our instruments fall silent and our questions fade into the accumulated dust of centuries. There is something almost restful about that immensity, is there not? Something that suggests the burden of being known, of being observed, of mattering in a measurable way, is not actually as universal a necessity as we have been trained to believe. The rogue planets that drift through the galaxy tonight, this very moment, even as you listen, are not lonely in any human sense. They have no minds to suffer isolation, no hearts that ache for connection. Instead, they move in a state of perfect equilibrium, balanced between the gentle gravity of the galaxy itself and the vast emptiness that surrounds them. They carry whatever heat remains from their formation, that slow ember cooling infinitesimally over billions of years, warming perhaps a hidden ocean beneath an icy shell, sustaining perhaps unknown forms of life in the absolute dark. Or perhaps they remain as sterile as the vacuum they pass through. We may never know. And that unknowing is not a failure of science. It is, rather, a gift. It is a reminder that not everything in creation needs to be mapped, measured, or made to serve our curiosity. What these solitary worlds offer us, as we sit here in the darkness of our own night, is a kind of permission. Permission to exist without an audience. permission to move through life without needing to orbit around some central source of meaning or validation, permission to simply be, as these planets simply are, in whatever form that existence takes. They drift through the cosmic dark with no path predetermined, no destination fixed, no purpose beyond their own quiet continuation. And in their drifting, they compose a kind of cosmic poetry, a slow waltz of matter and gravity, played out across distances so vast that no human mind can truly encompass them, yet played out nonetheless, with perfect regularity and perfect indifference to whether anyone is watching. The future will bring new telescopes and new surveys, more sensitive eyes turned toward the sky, more sophisticated algorithms designed to tease the signals of rogue planets from the vast background noise of the universe. Roman Space Telescope will add thousands more to our catalogue. Other missions yet unnamed will follow. Our maps of the galaxy will grow richer with detail, our understanding more refined. But even with all those advances, the essential mystery will remain. The rogue planets will still move mostly unseen. The darkness will still hold its secrets, and the universe will continue on its path, vast and indifferent and beautiful, asking nothing of us except that we pause occasionally to wonder at it, to acknowledge its presence, and then to let it simply be. As you lie now in your own darkness, you are surrounded by truths on an almost incomprehensible scale. Billions of worlds are moving through the void around your own small planet. Right now, at this moment. Most will never be seen by human eyes. Most will never be named. Most will make their slow journey through the cosmos in complete obscurity, and this will be enough for them. There is something deeply soothing in that recognition, something that allows the mind to finally release its need to grasp, to catalogue, to understand. The universe does not require our understanding in order to exist. The rogue planets do not require our attention in order to justify their presence. They are there, in the dark, cool and distant and strangely complete in their solitude. And so we leave them now, as we must leave all mysteries eventually, to their endless drifting. We leave them to their silent journeys, to their hidden oceans and their residual heat, to their slow cooling across the eons. We acknowledge their presence in the darkness, honor the strange and solitary path they travel, and then we let them go, back into the quiet they have never left. There is rest in that letting go, rest in accepting that the universe will hold its secrets, that not everything needs to be known, that some of the deepest truths exist in the spaces between our knowledge, in the silence between the stars. And in accepting this, we too find our own kind of peace, our own small solitude within the vastness, our own quiet drifting toward sleep.